Well, it's that time of year where we start to introduce some applications of differentiation. In particular, we usually do some economics examples and some physics examples. And this video is about the physics. We're going to talk about the calculus of motion. So let me start by introducing how we represent motion with functions, and then we'll talk about where calculus comes into play. So we need to start this discussion by talking about position. And typically when we talk about motion, we start by talking about the motion of a particle moving around on a number line. So I'm going to draw out a little number line here. You've seen this before, hopefully. And I'm going to introduce to you a little particle, which is this red dot. And we're going to create a function that represents the position of that dot at a particular time. And we name that function s of t. And I usually draw it with a cursive s because my print s's sometimes end up looking like 5s. So the position function s, or s of t, is a function that tells us where this dot is located at a particular time. For example, since I've started my red dot there at 2, I would say that s of 0, which is my initial starting time, would be 2. And let's say 2 seconds later, my dot ends up at -3. So something happened over time and I ended up down here at -3. Then I would say s of 2, which would be 2 seconds later, my position is -3. And usually what we have is a formula, right? Some function where we know where s is based on that function. So, it might be something as simple as s of t equals 4x plus 1. 4t plus 1. The independent variable here is time. So we use t in these equations. So if you, in this example, where this function is written here, s of 0 would be 1, s of 2 would be 9, and so on. But there could be any function over here telling us the position of our particular particle at any given time. And the initial position is when time equals 0. So I'm just introducing to you the idea of a position function, which is named by the letter s, the function s of t. I suppose that's because the letter p was taken by pressure, so we use s for position. But I don't have a clear example of that's true. I don't have a source for that particular statement. Anyway, enough babbling. Let's move on to talk about changes in position. Now that you know about position, we can have a discussion about displacement. And displacement you might think of as distance traveled. It's a change in position. So hopefully in math and science, sometimes we indicate that we're doing some sort of change by using a little triangle, a delta symbol in front of the s. So delta s, the change in position, is just the position over time minus the starting position. So the end position minus the starting position. That's what this is showing you. Typically, I write that as s of t2 minus s of t1. This is another way to write it, f of t plus delta t minus f of t. But we'll usually write it as s of t2 minus s of t1. And then if you want to talk about average velocity, this is kind of like average rate of change. It's not kind of like it, it is like it. Average velocity then becomes just that simple slope calculation. It's the displacement divided by the amount of time. And so you can see here that we've taken delta s over delta t, and in their notation, it's f of t plus delta t minus f of t over delta t, but you might think of it as s of t2, s of t2 minus s of t1 over t2 minus t1. And this is our VAV, which is our average velocity. And if you write it in this context, it looks a lot like y2 minus y1 over x2 minus x1. It's the same kind of a calculation. This is the average velocity. So something like if you're driving from your home to school, you start out in the stopped position in your driveway, then you speed up to your traveling speed, which might be 55 miles an hour. At some point, you might come to a stop sign, and you'll slow down and stop, and then speed up again before you get to your destination. So you achieve a bunch of different velocities over the course of that trip. But your average velocity is how far you traveled from home to school divided by how long it took. And that's what we mean by average velocity. And I'll show you an example of those calculations in a second. Okay. Now we can start talking about the calculus of these problems. So you already know that instantaneous rate of change is actually just a fancy way of saying the derivative, right? A derivative function will help you figure out the instantaneous rate of change of a function at any given point. And when we're talking about the instantaneous rate of change of position, we're talking about velocity, the velocity function. So here we're defining v of t to be the derivative of the position function s with respect to t. And then, of course, you know that the derivative is defined as the limit of the difference quotient. What I like to write is v of t equals s prime of t. Right? Velocity is the derivative of position. And so earlier when I told you that s of t equaled, I thought it was 4t plus 1, the derivative then would be 4. Now that's not very interesting, but it's a simple linear function for the position. But you can see that when we take the derivative of the position function, we get velocity. Now, velocity in physics has direction. So the sign on the velocity tells us about that rate of change. And in particular, what it means is when your velocity is positive, you're moving forward, and when your velocity is negative, you're moving backwards. So keep that in mind, that velocity does have a sign. Moving forward is different than moving backwards. Okay, let's talk about speed. So we just mentioned that velocity has a sign, that moving forward is different than moving backwards. So you can have negative velocity. But when we want to just talk about the speed, it's simply the absolute value of the velocity. And so I usually write it just like they've written it here. There's no reason for me to rewrite it. The speed is just the absolute value of velocity. And so when we do our speed calculations, don't forget to take the absolute value. If you continue doing derivatives, you end up finding some other quantities. The rate of change of velocity is called acceleration. And for us, that just means that we make a new function called a of t, which is the derivative of velocity. And so if we're following my other notation, a of t would be v prime of t, and that means that would be s double prime of t. And I don't know if they speak about this much in physics class, but there is a rate of change of acceleration called jerk. And that function is j of t, and it's the derivative of the acceleration. And I typically write that as j of t equals a prime of t, which would be the second derivative of velocity, which is the third derivative of position. And I like this one because I call this S triple prime. And whenever I want to insult somebody and call them a jerk, I'll call them S triple prime, and then maybe they won't know what I'm talking about unless they've taken physics and calculus. So the idea here is that we have this position function. When we take the derivative of the position function, it gives us a velocity function. When we take the derivative of the velocity function, it gives us the acceleration function. And if you take the derivative of the acceleration function, you get the jerk function. And these are all just slope machines, right? You plug in a time and out pops the value for that particular measurement. So if you want to know the velocity of a particle at 2 seconds, then you plug in 2 and it pops out. If you want to know the speed, don't forget to take the absolute value after you get the velocity. Let me just show you some examples, and I think that'll bring all this stuff together. We're really just taking derivatives and then plugging numbers in. So as you start your exercises, you'll see that in exercises 1 through 6, you're given the position functions s of a body moving on a coordinate line with s measured in meters and t in seconds. And we are going to be asked to do A, B, and C for each of these problems. So we're going to find the displacement and average velocity for a given time interval. We're going to find the body's speed and acceleration at the endpoints. And we're going to find out when the body changes direction. And I'm going to work on number 1 here in the example. So for number 1, to find displacement, for letter A, part 1, number 1, part A, displacement would be, I'll just call it D equals S of 2 minus S of 0, because that is S of T2 minus S of T1. And so let's see, when I plug a 2 in, I get 4 minus 6 plus 2, that's 0, minus, when you plug in 0, you get 2. So that displacement is negative 2. That means over the time interval, I went backwards 2 units. And since the time interval is 2 seconds, that means my VAV, my average velocity, is going to be S of 2 minus S of 0 over 2 minus 0. So that's going to be negative 2. We already calculated that. And then 2 minus 0 is 2. So my average velocity is negative 1. Since they told me S is measured in meters, I should say that this is negative 2 meters, and my average velocity is negative 1 meters per second. For letter B, we're asked to find the speed and acceleration at the endpoints. To get speed, I need the velocity function. So I'm going to figure out v of t first, and I just do that by finding the derivative. So the derivative of s is going to be 2t minus 3. And then to get the speed, I'll do the absolute value. To do the acceleration, I just take the derivative of the velocity, which is 2 in this case. It's not always a constant, but whenever you have a quadratic for the position, it's going to be a constant. Okay, so we need to find the speed and acceleration at the endpoints. So the endpoints are 0 and 2. So v of 0 is going to be negative 3. And that means that the speed would be 3. And that's meters per second. And v of 2 is going to be 4 minus 3, which is positive 1. Absolute value of 1 is 1 meters per second. So that is the speed at 0 is 3 meters per second, and the speed at 2 is 1 meter per second. And the acceleration at both of those endpoints is 2. So we're okay there. We don't need to change that one because no matter what time you're at, the acceleration is always 2. So for letter B, we get these 3 answers. For letter A, here's the displacement, and here's the average velocity. And then for letter C, it says, when, if ever, does the particle change direction? Well, the only place that it might possibly change direction is if the velocity ever equals 0. When you're moving forward, you're moving in the positive direction. When you're moving backwards, you're moving in the negative direction. So the only place where you have changed from positive to negative could be at 0. So the way we find the candidates for places where it might change direction is we set v of t equal to 0. In other words, I do 2t minus 3 equals 0, and I find out that my candidate is t equals 3 over 2, or 1.5. Now here's how you figure out if you've changed direction or not. You have to take a look at what happened before 3.5 and what happened after 3.5. And we've already done that because, take a look right here, we computed the velocity at 0 to be negative, meaning it was going backwards. And then at 2, it was positive. So the velocity went from negative before 1.5 seconds, and it was positive after 1.5 seconds. So it did change direction at that point. So at 1.5 seconds, the body changes direction. It's not enough to just set the velocity equal to 0. You have to also check and make sure that the velocity changed from positive to negative or from negative to positive. Okay? It's not enough to check that it equals 0. So we did both. I calculated the value, which was at velocity 0 at 1.5 seconds, and I checked to see if the velocity changed from negative to positive or positive to negative. Okay, so you'll be working on problems from in 2 through 6, but this was problem 1 as an example. Here's another example, and in this case, for time t greater than or equal to 0, which makes sense because time's usually not negative. We're given the velocity of a body moving along the s-axis, and that velocity is v equals t squared minus 4t plus 3. And in letter A, we're asked to find the body's acceleration at each time the velocity is 0. So there's really two things going on here. First of all, we got to find out when is this thing, when does it have a 0 velocity? And then secondly, what's the acceleration at those times? So let's go ahead and attack letter A here. My v of t is t squared minus 4t plus 3, and the way you decide when that equals 0 is you set it equal to 0. This is a quadratic, so I'm going to use factoring to solve this equation. This looks like a t minus 3 and a t minus 1, and that means that the velocity equals 0 at t equals 1 and t equals 3. So I need to find the acceleration at 1 and at 3. A of t is the derivative, which would be 2t minus 4. So I want to do a of 1, and that would be 2 minus 4, which is negative 2 meters per second squared. Oh man, what am I doing here? Meters per second squared. Actually, I don't know if this is meters and seconds, but I'm going to make the assumption when they don't indicate it that we're doing meters and seconds. And the acceleration at 3, a of 3, is going to be 6 minus 4, which is positive 2. So that's 2 meters per second squared. Letter B says, when is the body moving forward and when is it moving backwards? So we're actually going to use some information from letter A to help us. As this thing travels, it starts out at time t equals 0, right? We start, and the clock starts ticking, and when we get to 1 second, our velocity is 0. And when we get to 3 seconds, our velocity is 0. And then we just keep traveling. So what we need to find out is what's happening between 0 and 1, what's happening between 1 and 3, and what's happening after 3. And so usually what we do is just compute the velocity over in this section somewhere. And so I can do that by just plugging in 0. I can just find v of 0. V of 0 happens to be 3. So that means that my velocity is positive, so I'm moving forward over here. In between 1 and 3, I can compute v of 2 and see which direction I'm going. V of 2 is, that's 4 minus 8 plus 3. That's a negative 1. That means I'm moving backwards because that thing is negative. And then if I want to find out what happens after 3, I could compute v of 4 or v of 5 or v of 6 or whatever. When you plug a 4 in, that's 16 minus 16 plus 3. That's 3. That's positive, so this is forward again. What we're actually creating here is something called a sign diagram. We'll talk more about that later, but essentially we're positive between 0 and 1, negative between 1 and 3, and positive after 3. And so when I answer this question, I'll simply say that I'm moving forward for the first second and after 3 seconds, and I'm moving backward between 1 and 3. For letter C, when is the velocity increasing and when is it decreasing? So to figure that out, we need to talk about the acceleration because we're talking about the change in velocity. When acceleration is positive, our velocity is increasing, and when acceleration is negative, our velocity is decreasing. So for that, I need to take a look at my acceleration function, which is 2t minus 4. I'm going to set 2t minus 4 equal to 0, and I find out that at 2 seconds, my acceleration is 0. That indicates that it's possible it could change from positive to negative at that point. So I'm going to basically do the same thing I did on the last problem. I'm going to draw a little picture here. From 0 to 2 seconds, we already have a calculation that our acceleration is negative. That means that the velocity is decreasing, right? Because a of 1 was negative 2. And we did a of 3 was positive 2. And that means that the acceleration is positive and the velocity is increasing. So I would say that for the first 2 seconds, the velocity is decreasing. Means that number is shrinking. And then after 2 seconds, we're increasing again. And that makes sense based on these calculations here. We started at 3, we went down to negative 1, and then back up to 3 again. So we were decreasing and then increasing. And we've answered all 3 of the letters for this problem. I've got one more example for you, and then we'll shut this video down. So here we have a rock thrown vertically upward from the surface of the moon at a velocity of 24 meters per second, which is about 86 kilometers per hour. And it reaches a height of S equals 24t minus 0.8t squared meters in t seconds. So this is the position function. Instead of traveling along a horizontal line, we're traveling along a vertical line because something was thrown up into the air vertically. Eventually, it's going to come back down. We are supposed to find the rock's velocity and acceleration at time t. Whenever it says at time t, when they're not given a particular value, it means they just want you to write out the function. So we're essentially looking for velocity and acceleration. So velocity is, this is for letter A here, velocity is the derivative of this position function. So it's going to be 24 minus 0. Let's see, not 0. 2 times 0.8 is 1.6 t. 24 minus 1.6 t. And the acceleration, a of t, is the derivative of the velocity, so that's just going to be negative 1.6. So there's our 2 functions. And the acceleration here is due to the gravity on the moon, as it says. So we're done with letter A. For letter B, how long does it take the rock to reach its highest point? So when you throw something straight up in the air, it's traveling with a certain amount of velocity, but when it turns around and starts falling, it actually stops for an instant before it starts coming back to the ground. So what we need to do for letter B, and I'll start doing letter B down here, is we need to set v of t equal to 0. And then we'll know when it started falling. So that means 24 minus 1.6t equals 0. I need to divide 24 by 1.6 to figure that out, and that is 15. So at 15 seconds, this thing reaches its highest point. It's thrown up in the air, straight up, and right before it turns around to come down, it stops. The velocity, right? For a split second, for an instant, the velocity is 0. And that's when it reaches its highest point before it starts coming back down. How high did it go? Well, to figure out how high, we need to do the position function. And we need to do position at 15 seconds. So we need to do S of 15. And so I'm going to do what? 24 times 15 minus 0.8 times 15 squared. And we'll compute that, and that equals 180 meters. At 15 seconds, this thing's 180 meters in the air. Letter D says, how long does it take the rock to reach half its maximum height? And so for that, essentially what we want to do is set S of t equal to 90 and then solve. In other words, 24t minus 0.8 t squared equals 90, which is a quadratic equation. So you've got some options. When you rearrange the terms here, you get negative 0.8 t squared plus 24t minus 90 equals 0. So you could try and factor that thing, but it's not going to turn out to be an easy endeavor. Instead, what you can do is just plug this into the quadratic formula or graph it and see where it crosses the x-axis. And I've already done that, and I found out that that happens at t equals approximately 4.39 seconds. So this thing reaches half its maximum height at about 4.39, 4.4 seconds. And I did that by setting the position equal to 90 and solving. And then finally, how long is this thing in the air? Well, this is actually a pretty easy question to answer. If it takes 15 seconds to get up to its highest point, it's going to take 15 seconds to come back down. And so the answer there is simply 30 seconds. It'll hit the ground after 30 seconds. So it's in the air 30 seconds. It's aloft 30 seconds. I guess they don't call it air because we're on the moon. But it's aloft for 30 seconds. And I just use a little bit of common sense there and what I know about parabolas being symmetric. And if it takes us 15 seconds to get to the highest point, it's going to take us 15 seconds to get back down. The other thing you could do is simply graph this this function and see where it crosses the x-axis, and you'll see it crosses at 0 and 30. So that's another example of applying these concepts from physics and calculus to solve some of these motion problems. Basically what we've learned is you'll have a position function to compute velocity, which is instantaneous velocity. You take the derivative of the position. To compute acceleration, you take the derivative of velocity, and then you'll plug in the values or solve those equations to answer questions about motion. That's enough for this video. Good luck on the problems you've been assigned, and let me know if you have any questions. Take care.